Pues estamos muy contentos en este festejo del tercer año de actividades de astrofísica de altas energías en el MCTP. Todo festejo trae alegría, también trae retos, también nos obliga a hacer una reflexión de cómo vamos, hacia dónde vamos, si está realmente llevando el camino correcto el centro y si va a cumplir sus metas como se ha planteado desde su creación. Entonces, la incorporación del Dr.Omar al MCTP forma parte de uno de los grandes pilares del MCTP. Me refiero de los tres ejes en los que se concentra el MCTP, que es la investigación científica, la educación avanzada y el intercambio y la movilidad. La contratación de profesores investigadores en el MCTP es una de las cuestiones más importantes, y en la primera convocatoria que lanzamos para contratar dos profesores porque se incorpora Dr.Omar y se declara desierta una plaza, y en la siguiente se incorpora Sara Kaufman. Pues casualidad, se da en el tema de astrofísica, pero también está creciendo el MCTP en otras áreas como la física teórica, y que se han incorporado profesores, otras vías como cátedras de investigación del CONACYT, que se incorporaron hace aproximadamente poco menos de un año, en octubre, dos profesores más, que es Jorge Mastache de los Santos y Xiomara Liquidos. Vía la modalidad adjunta y profesor temporal se encuentra Elías Castellanos y Celia Escamilla Rivera, que estaba aquí en ese momento. Entonces así va creciendo poco a poco el grupo, y bueno, es parte del desarrollo que tiene el MCTP. Vamos un poco más lento de lo que lo habíamos planeado, pero creo que vamos bien. A lo mejor hace falta un poquito más de vídeo o las fechas para las próximas convocatorias, desarrollar las otras áreas, que son 4. Por ahí ya empieza a ver cuáles son sus áreas de investigación. Bueno, pues el doctor Tiboya nació en Italia, estudió la carrera de física en la Universidad de Trieste y el doctorado en la Universidad de Padua. Ha hecho estancias postdoctorales y de investigación en diferentes instituciones de prestigio, como el Max Planck, por ejemplo. Ha estado también en el Instituto Nacional de Astrofísica de Milán, en Alemania también. Su área de investigación es la astrofísica de altas energías, rayos cósmicos, remanentes de supernovas, destellos de rayos gamma. Entonces es un experto, digamos, de la astrofísica. Participa también en diferentes colaboraciones internacionales, entre ellas el Hubble, en teoría. Entonces su currículum es muy amplio, que nos llevaría una semana que no completa. Esperamos mucho del profesor Tiboya, esperamos grandes resultados, y bueno, tiene más de 200 artículos, 240 artículos, alrededor de 13.000 citas, y es profesor de tiempo completo, profesor investigador del MCTP desde el 16 de agosto de 2014. Sí, me acuerdo perfectamente porque me tocaba estar en todos los procesos de contratación, las convocatorias. Es más, se presentaron 64 candidatos en la convocatoria. Entonces, le damos un fuerte aplauso al doctor Tiboya.
Una semana hablando muy rápido. el reporte completo. Antes de todo, gracias a todo el MCTP por organizar esta celebración de 3 años de actividades. Y vamos a, antes de todo, establecer el idioma. Si vado a hablar japoneco, Lucas, Rubén, tampoco Sara me van a entender. Si vado a hablar castellano, muchos de los japoneses aquí no me van a entender tampoco. Y ahora vamos a hablar el idioma universal de la investigación. Si me gusta o no me gusta el idioma universal de la investigación es el inglés, y de ahora vamos a hablar en inglés. Y los estudiantes deben entender este idioma para hacer este trabajo. So, we are going to speak very quickly, as Eddie was mentioning, a very short summary of the 3 years of activity of the MCTP High Energy Physics Group. And I hope to convince you that the activities are too many to be spoken in only 1 hour. And this is the outline that we will follow today. We will start with a very short preface and short history about the group. We will focus on the main research lines and the backbone plans. This includes international collaboration. It includes the big collaboration that you saw 2 examples by Lucas and Ruben today. And include the teaching, the didactics, so training the future scientists, the students. We will summarize very few for time limitation of the main achievement of the groups, and we will make a short conclusion of that. I mean, the short preface and history, actually the link between myself and the MCTP unit was started earlier than the foundation of the MCTP itself, when an important European professor, Professor Spilantini, is one of the main authors of satellites like Pamela and Nina, was the scientific ambassador of Italy in the Soviet Union for many years, introduced me to Professor Cepeda. And so I was informed about the very, very ambitious plan to build a small STP in the Central America region. And he was informed that I was searching, aiming for a permanent position since we were planning to make family. So in 2013, as Eddie was just mentioning, I was applied to the call for a research field professor in November, and I visited Tuxtla Gutierrez for my first time. Actually, it was the first time I was visiting Mexico. And I had the occasion to discuss with many details with MCTP directors, so with Dr. Cepeda and Dr. Eli Santos. On March 2014, Anulfo, on behalf of the MCTP Scientific Council, is worth to mention here that the MCTP Scientific Council is chaired by Nobel Prize winner of Sheldon Glashow, so one of the most important Nobel Prize winner of the history of physics, and he got Nobel Prize on the standard model of elementary particles. So I quit my position in Australia, and this was the birth of the high energy group. As Lee mentioned, the greatest shot of the group was 1 year and a half after, when the group gained a second full professor, that is Dr. Sarah Kaufman, who was already collaborating with us during the first year of activity of the group, and she's internationally well-recognized expert on active galactic nuclei and X-ray astronomy. So, what are our main research lines? I was simply asked to continue my research activity and to try to create competitive research, internationally competitive research groups here in Chiapas. The main incidents of my career were about high energy astrophysics and cosmic ray science. In particular, the topic that took a major part of my scientific career was about the origin of cosmic rays, the question you asked before, where they come from. I will speak later about this if you want. And I can speak 10 days consecutively about this if you are not satisfied about the very short shot that I will show you now. This includes mainly supernova dynamic pulsar nebula and identified energy sources, but as already seen in the talk of Lucas, this oblige us to extend our field of view to extragalactic objects, and in particular to active galactic nucleus, star-burst galaxy, and camera burst. Another activity of our group, very minor activity of our groups, is about gamma ray and the X-ray binaries, galactic binaries. So let's make a quick overlook about the possible accelerator. We are working on studying the natural accelerator of particles we have in the universe, that, as Ruben mentioned, can reach energy much higher than the accelerator we will be ever been able to build on the Earth or within our galaxy. So let's start with extragalactic astrophysics, and we work a lot on active galactic nuclei. And in particular, we put a lot of effort on two particular subclasses of AGNs that are blazers, that are the AGNs that point directly to us, and other light at one galaxy. And I will say a couple of words about this. AGNs have a supermassive black hole, more than 1 million of solar masses, and a hot torus of matter spiralizing and accreting onto this black hole. This, above a certain level of mass of the AGN, gives the birth to incredibly powerful relativistic jets. I mean, the matter in the jets is very close to the velocity, the speed of the light in the vacuum. So, as correctly Lucas mentioned before, we think that these are indeed some of the most efficient particle acceleration we have in our universe. And the important thing that is one of the main backbone of the creation of the group is that this kind of object emit over the full electromagnetic spectrum, starting from radio, very low energies, to the most extreme gamma rays. And this is why I started this very short overview with AGNs. In fact, here you see M87, so one of our most powerful neighbors. And you see how the jet of M87 will appear in radio, with a VLA, in optical, with a Hubble Space Telescope, and X-ray in Chandra. This example is very simple, very trivial, but extended to every other aspect we are dealing with in our research group. This means galactic science. So, in order to study the non-thermal emission of this cosmic acceleration, multi-wavelength studies are mandatory nowadays. The time of single-band astronomy is dead since 1 century. Sorry to tell that. So, if we want to understand how the accelerator works nowadays, we must have the full picture of how this accelerator behaves in every energy range we can investigate. So let's go to galactic astrophysics. Major part of our activities is about the study of supernovae remnants, pulsar nebulae. Here you see an example of Cassiopeia A and Carbon Nebula. Both are supernovae remnants. So what is left behind from very powerful explosions? These two cases are the most explosive, most powerful explosion in our side of the galaxy. And this guy, in the Club Nebula, already shown by Ruben, is also a pulsar nebula. So it's filled by relativistic electron positrons that are emitting very high energy, as shown by the whole spectrum of it. The big family that contains is indeed unidentified sources. More than 50% of the TV sources, tera-electron sources, gamma ray sources are still unidentified. We see them, they're bright, we don't know what they are. And if you go to GV, so satellite science, this number is even increasing. It's more than 60% of the GV gamma ray sources are identified. We see them, they are very bright, we don't know what they are. 90% of them are thought to be supernovae remnant or pulsar nebula. And we are going more in detail in the final part of the talk on this aspect. I must say that probably the most known activity of our group is related to the origin of cosmic rays. What I mean with the origin of cosmic rays? The cosmic rays have been discovered more than 1 century ago by the German Jesuit physicist Theodor Wolff, by the Italian physicist Domenico Pacini, and by Victor Hess, who finally got the Nobel Prize for the discovery of cosmic rays, because his experiment was convincing almost everybody that this was true. Almost everybody means everybody in the world but of Millikan, very famous American scientist, the father, the one who discovered the electron, was not convinced that cosmic rays was having extraterrestrial origin, and worked really 40 years to prove that cosmic rays did not exist. Ironically, the term cosmic rays came indeed from Millikan. However, in the Nobel Prize justification, Victor has got the Nobel Prize for the intuition that the radiation he could measure was of extraterrestrial origin. And this intuition was already present from the work of Theodore Wolff, that was speaking for the first time about Hohenstrahlung, so radiation coming from above, and by the water experiment of Domenico Poggini. So we know them since 100 more than 1 century, and we still do not know where they come from. The standard model tells us that until 1 PeV, 1 peta-electron volt, they should be accelerated in supernovae energy shells. Okay. So when I will speak later about the standard model of cosmic ray origin, I will speak exactly to this point. The very famous monograph book of Ginsburg and Sidorowski in 1964. But not only. At least 10% of the kinetic energy of the supernova explosions must go in cosmic ray acceleration to prove to justify the local density of cosmic ray that we measured in the neighborhood of the Earth. Okay? This is proven only by one paper, of which we are author, and we will speak later about that. Yeah, we have seen by Lucas' presentation the spectrum of cosmic rays, and you see that you can measure it in different ways. Directly, with Pamela IMS, satellite balloons, or using the atmosphere, like Piero Gedad as a big detector. And we will speak about GEM also during this talk, but also indirectly. So to see gamma rays and neutrinos that are accelerated and are produced by the acceleration at the location of acceleration. So exactly on the supernova diamond, on the plasma nebula, or the active galactic nuclei. Another thing about nomenclature, today when I will speak about energies, I will speak high energies, I will speak about energies above 1 GeV, 1 giga-electron volt. And when I will speak about very high energy, I will speak about energies above 1 TeV, 1 tera-electron volt. So I mentioned that multi-wavelength astrophysics is the only way to do our job nowadays. And in fact, this is crucial to understand the physical emission process. So where do we work? In our high-energy astrophysics group at MCTP, we work mainly above the kilo-electron volt, so above the soft X-rays. We work mainly on X-rays and gamma rays, from satellite and from ground-based observatory. How? Fortunately, as you might remember, the atmosphere is shielding us from major parts of the radiation that is hitting our planet. Actually, it blocks everything but our small window in the visible light, so the peak of our stars, the sun, and then the radio. So either we go outside the atmosphere with the satellite science, or we use the atmosphere as a detector with the Cherenkov telescope, so imaging Cherenkov telescope, water Cherenkov telescope as Oak, or extensive air shower array like Piaget showed that by Lucas. At MCTP, actually, we do both. So, what is the long-term weapon plans? A very few words about this. I'm not used to so much to speak about constructing, building, politics, and this kind of thing. I like more about speaking about science. I'm more used to do that at least. So, the question was how to develop in a short time a competitive high-energy group which can be internationally competitive and renowned. So the short-term construction must come inevitably from international collaboration, which include both small group of people, 2, 3, 4 people, that is common between the theorists and the astronomers, but also the big international experiment and collaborations, the Hope and the Shape. In fact, only full multivariate studies can answer the currently open question of the field. Sorry if I'm stressing you a lot on this point, but this is one of the main points of the backbone of our of building our research group. Moreover, remember that these are necessarily very big collaboration of more than 100 people, because this experiment cost millions of dollars, especially the satellite. It's a factor of 100,000 more satellite experiment than spectrogram based. And so this is basically far beyond any means of any national institution in the world. Even the richest country have a lot of problems to build by themselves this kind of experiment. The long-term construction instead should come from selecting the future experiment. We make a bet. We say this experiment is the experiment that will be the breakthrough in the future. And the very, very long term construction is coming from training the future scientists, so the ones that now are you, the students. And we will speak about that as well. So another crucial task is increasing the firepower of the group. But this, of course, is not a task that can be done only by the energy astrophysics group alone. This is a general task of all the people at MCTP and more in general all the people of UNACH. And that to make our institutes renowned internationally, more attractive, to attract the best scientists of the world here to work with us. And in this way to increase the firepower. We are doing really a lot of activity, and we need more people to do that. As mentioned, the greatest shot for us was the hiring of Professor Sarah Kaufman. And regarding postdocs, we are working in close collaboration with the faculty, in particular with Dr. Cesar, and we are trying to hire some international experts via the Corpo Academico of the faculty. In particular, now we have on the desk internationally recognized expert of magnetic electrodynamics and international expert of misaligned active-galactic nuclei. Okay? That is, at the end, our selected candidate. We are trying to make a convincing job offer to them to be able to hire them. Okay? And this is the task that is becoming more general and beyond the possibility of our research group. So, I mentioned the international collaboration that are the biggest shot to develop quickly a competitive research group. So basically, regarding the international collaboration, we took to Chiapas the collaboration that we had in the past. We worked with many colleagues from almost all the continents of the world, for instance, from Asia, Japan, China, Taiwan, and India, from South Africa, and from USA, and in particular from Europe. Even if it's a small country, a small region for territorial, I mean, as Lucas was mentioning, the density of a researcher is probably, without problem, is the highest in the world. So, particularly Italy, Germany, United Kingdom, France, Ireland, Slovenia, Croatia, Portugal, Spain, and Austria. Once here, we could start strengthening our collaboration with United States colleagues and creating new collaboration with Mexican and Costa Rican colleagues. And of course, we are going on increasing also our transcontinental collaboration. In 2 months from now, I'm invited to Serbia in Europe, who in the direction of cosmic ray origin has a very big school, a very nice school historically, and they are developing some very challenging working plan on that. So, but as mentioned, it is not enough. To build a competitive energy group, we need to take here some of the best world experiments. Okay? And this is a very challenging work. And we don't want to take some random experiments, but we want to have coverage in wavelength as complete as possible for the reason mentioned before. And so we put particular attention in filling the gaps of wavelength that we had in our expertise. So, a very short summary of the activities, and I will go a bit more in detail in any of these wavelengths. I mentioned that we work above the TeV, so the key electron volt. So at X-rays, we work with Chandler, X-Newton, and Swift satellites currently. And we are members of the future satellite of X-ray astronomy, as it's called, that is called Athena. How the X-rays, 100 TeV and soft gamma rays, we are a member of the E-astrogram. I will spend more slides to speak about this, because this, according to me, is the key issue for the future. The future of physics cannot escape from this waveband. Most of the current open questions in astrophysics will find their answer inevitably in this energy band. At the GeV gamma rays, we are in the very famous Fermi-Lab satellite. And GeV gamma rays, we are dominant members of imaging atmospheric and telescopes, such as imaging and CTA. But since we become here, we concentrate a big part of our energy on Hope. And you have seen just now a very nice presentation of Hope result by the web. And moreover, we are extending our expertise to ultra energy conic rays with GEM and HEO. So that is the future experiment that will go even to higher energies than the Auger you just saw a very nice presentation by Lucas. So we are also a member of smaller international collaboration labs such as LAGO and FACT, and we are dominant of FACT, but they have mainly deductive purposes, so we don't put much scientific effort in that. So let's go a bit in detail in these experiments and this waveband that we have mentioned. We work a lot with X-ray satellites, in particular with X-Newton, the European satellite launched in 1999, Chandra, the American instrument, launched in 1989 as well, Swift launched in 2004. The first is the most sensitive X-ray instrument in this band existing. The second is the most precise X-ray satellites existing, and Swift is the most sensitive for transient events that are the one shown by the right. What's the advantage of this experiment? We have huge data, archives data available, and most of them are not yet analyzed. So this is a gold mine for student bases. I mean, our students, as you will see later, 3 of the 4 theses that we currently are advising are based on this kind of studies. Moreover, X-ray analyses are more established, since this field is older than gamma rays. They are easier to perform than gamma rays, and they request less time. Okay, so they are particularly suitable for bachelor and master thesis. Okay. So, moreover, it's not impossible. Means that we have every proposal, if done well, has more or less 50% of being successful accepted. Even if in 2015 our group had 50% success rate, so more than 3 times the usual limit, to get new observation on interesting sources. And we will spend some words on that. So how does high X-ray astronomy astrophysics works, the instrument? So X-ray photons pass through optical mirrors, since they have much higher energy. So in order to be able to detect them and study them, you simply use reflection with very low angle. And this you do with combining hyperbolic and parabolic mirrors into a focal plane. So the combination of parabolic and parabolic mirrors is called Walter mirrors. So here is how we would like an X-ray observatory in a section. This is X-Newton. You see that there are a lot of concentric circles. These are the mirrors that are schematized in this way. So they are concentric and going to a focal point that is here and is here. And in the case of X-Newton, we are dealing with 58 mirrors, and you see from the length of the satellite how that they really have to be parabolic. It's much longer than water. So I was mentioning that it's very important to put the basis for the future development of the group as well. And in X-rays, we become active members of Athena, that stands for Advanced Telescope for High Energy Astrophysics, that is considered the future of X-ray astronomy. Currently we are involved in the advanced planning phase of this satellite. The most important point of the satellite is that this satellite was selected by ESA. This is the yes or no for satellites. You work for many years on a satellite after the space company, that can be ESA, so the European Space Agency, NASA, the American Space Agency, the Italian Space Agency, the Mexican, and say no. And your 5 years of work goes in the trash. This was selected, so all the work we did on this is not trashed, but is becoming actual. And this satellite is due for launch in 2020. So there are two instruments that basically will take X-ray astronomy to a different level of sensitivity, and it will basically study everything from solar system bodies to the most distant object known, okay, with unprecedented X-ray sensitivity. Let's go to the one that I consider probably the most intriguing wavelength that we are working on. I did work for 2 years in the past on a satellite called Grupo. You will never heard about that. You will never hear again about that because the European Space Agency says no. So 2 years of job was going in the drain basically. Why is it so important? First of all, because we don't know anything about this energy band. This is called, or we know very few about this energy band. This is called the energy gap. And this means basically that in the IRIS band, so the X-ray band that we just saw, we know more than 1,350,000 known steady X-ray sources and transmitters. On the other band that we will see in the next slides, so the GeV gamma rays, we know more than 3,000 GeV gamma ray sources. But in this band, we know only 40 sources due from Compton instrument on board in the Compton gamma ray observatory. So filling the gap and with a high precision must be the task for the satellite community in the future. This is my point of view, of course. Moreover, in this energy band, everything is studied, and all the answers that we couldn't have seeking for will find the confirmation in this energy band. In particular, you see here is basically all the aspect of astrophysics of everything of astrophysics. We are interested on nucleosynthesis in those vapors. At this energy, so from 100 keV to tens of MeV, you map the lines emission of aluminium 26, titanium 44, and iron 60. So basically, you map all the history of our universe. The decaying time of these elements are very different, going to the very young iron 60 to the very old aluminium 26. Passing to the titanium 44 that is particularly interesting for middle-age supernova explosion, middle-age supernova emergence. Moreover, we will map the 511 keV region. This means where the positron and the electrons annihilate. So with this kind of experiment, you will be able to map the location of all the electrons in our universe. Okay? This is particularly important, for instance, for the dark matter study that Ruben was mentioning before. When you know that the electrons are there, you subtract and you see what is left. If there is something left, and I doubt it, there is dark matter. Okay? And in particular, can give a big smoking gun about the origin of cosmic rays. I give you a very old paper of mine if you want to go deeper. Basically, in this paper, I was showing how the quasi-spontaneous nuclear excitations of some elements like oxygen and in particular carbon-12 will give rise to a peak in your spectrum, and this will give you 100% proof of the cosmic ray acceleration in this place. When I speak about cosmic ray acceleration, I speak about protons. We already know from satellites where the electrons, so the electron deposits are accelerated. What we mean is only the 90% of cosmic rays is the protons. This is the key issue, and when I speak about cosmic standard model for cosmic for the cosmic ray origin, I'm speaking exactly about protons, okay, to not be misunderstood. So the future experiment that should do this job is called e-astrogam, and we became an active member of e-astrogam as well. The nominal energy range is from 300 MeV to 3 GeV, so exactly the energy range that we want, providing a very good overlapping with a very successful Fermi lab. Important, the mission has been currently accepted in all the steps of the European Space Agency M5 call, but the call is not over yet. We know that only 25% of the experiment that currently in the race will win. So we actually build and put in space. So another major activity we had, major basically because you will see it in the next slide, is the Fermi satellite. Was launched in 2008. And the most important instrument on board is the Alta telescope from 20 MeV to 300 GeV. And you already heard of it because it's probably the most successful instrument ever in astrophysics. The second instrument, the gamma ray fast monitor, is also flying on board the satellite. How does it work? This is basically a pair of conversion telescopes. You cover everything with an anti-coincidence shield. This is quite ironic. I mean, for every gamma rays, we have 10,000, 100,000 protons. And for our study, this is our background. So you have to reject it as much as possible. So the anti-coincidence shield of Fermi is a plastic scintillator of Vicon 503, if I remember correctly, and is shielding us from 99.994% of the protons. The gamma rays enter, not recognize the charged particle, interact in the tracker. This is a particle tracker like the one we are used to see in particle experiment on the Earth, creating a couple electron positrons, and these two particles are made shower in a very thick and dense calorimeter to try to detect the energy of the incoming particles. With this, we should be able to get as precise as possible the direction of the gamma ray and its energy. So Fermilab was very successful. We was winning the Rossi Prize in 2011. I mean, it's one of the most important recognition in our field. And there are many scientific discoveries and success. Here we cheat only one, the proof that the standard model of cosmic rays works. This happens from 11, also including me, on the supernova element called Tycho. Tycho shows that the model works. The problem is that this is the only supernova element where the standard model works. The very and only. All the other cases has some issues. Or efficiency, the protons acceleration is not efficient enough, or they simply do not show any trace of proton acceleration, like the one that probably was the most promising target before the launch of Fermilab, that is LXJ1713. I'm working in this experiment since more than 13 years, so since before the launch, in the building phase of the satellite, and since 2008, I became an affiliate scientist to Fermilab. So let's go to Fermilab TV astronomy. Fortunately, Ruben already showed it very nicely, so I can go very quickly on that. A gamma ray enters the atmosphere, make an electromagnetic shower, the particles go quicker than the light in the medium, and they make giant of flashes. You put a set of telescopes down, you can detect the shower, you study the shower, and thanks to this you recognize the gamma rays. If you put two telescopes, for instance, you have immediately a precise recognition, the construction of the incoming direction. This is called the stereo approach and is used by Hess and Veritas instrument. We worked a lot, both me and Sarah and Hess in the past when we were in Germany, and give you an easy, precise construction of the direction, but it's even more important for the black hole injection. At the sea level, in 1,000 meters for atmospheric physics purpose is sea level or less, but of a bit at the optical scene. The best, the worst background you have is given by muons. Okay? As you see, as you remember probably from single canonic band, etc., the Cherenkov flashes of muons have a shape of a ring. But this happens if the flash happens very high in the atmosphere. If it is very low in the atmosphere, it's still a ring, but your detector cannot distinguish the ring from an ellipse of an electromagnetic shower. If you put a simple multiplicity and you oblige your system to see the event in at least 2 telescopes, you get immediately 100% rate of your vector. There is another approach used by MAGIC that is making much bigger telescope to be able to detect a much fainter showers and go very much lower in energy. The success of both systems obliged MAGIC to build a second telescope, as you can see in the picture, and you use the stereo approach to add the multiplicity to the system if you prefer, and has to build S2, so an enormous telescope in the middle of the Hess array. And the next steps for all imaging atmospheric Cherenkov telescope coloration is the Cherenkov telescope array, CTA. So an enormous array with hundreds of Cherenkov telescopes, small, middle, and big size. We are members, even if we were active until 2015 and 16, now we are dormant members of MAGIC and CTA. I mean, we have too many activities and we need more firepower to be able to accomplish all the duties that we have. So you have to get rid of some of them partially until you can get more firepower to be able to be really active involved in the instrument. I think that it's not worthwhile to be active, to involve in an instrument where you don't work directly. So we decided to go in sleeping mode for this collaboration for the time being. But if instead of putting a Cherenkov array, you put a water Cherenkov array, as Ruben showed before, you have 2 main advantages. First of all, you have a full sky instrument. And secondly, you are not limited with the cycle. Cherenkov telescopes cannot observe in moon time. Of course, they cannot observe in the daytime, but not even when the moon is close to the horizon. For the most sensitive cameras like the Hess one, this is enough to completely burn off the to multiply of your camera. Okay. Instead, we hope we do not care if it's day, night, raining. Everything is good for us, and it's a very big advantage, because even if our sensitivity, nominal sensitivity, is not high enough as Cherenkov telescope, we observe every day, every night. So our statistics is increasing much more rapidly than their statistics. And in the future, our group will be more and more involved in POSAP if we will ever get the funds to build it. No? So let's speak about the last big international collaboration we are working on. Also for this, I'm very happy that that Lucas accepted our invitation. He spoke very nicely about all the aspects of this, so I don't have to go into details. GEM is basically doing what OJ is doing, but from the outer space. So you look at the ultraviolet photons of the extinct air shower in the Earth atmosphere from the ESS, from the International Space Station. Okay? This is not built, this is also part of the future experiment in which we will hopefully become more and more involved. So the energy range is basically as much above the so-called ankle, that is almost a 10 to the 18 electron volt. So its nominal energy range is above some 10 to the 19 electron volts to the GZK cut-off energies tended to enter electron volts. And Lucas was already going into detail that. Thanks again to spare me this explanation. Last note that is randomly answer the other question you had before. As you have seen, we have direct and indirect approach. While the primary particles are important for things like the cosmic ray decomposition, okay, the gamma rays and the neutrinos. I mean, I'm one of the one that believe that the neutrino astronomy will be the future astronomy. Unfortunately, it's very far in the future, very far in the future. But I'm convinced that it will become the future astronomy. Have one big advantage: the gamma rays and neutrino are not deflected by the magnetic fields. Okay, so if you have a source accelerator of particles, in very few parsecs, the directionality of your incoming event is completely lost. Instead, if you see gamma rays and neutrinos, you know that there is acceleration is taking place. Okay? For this, the indirect approach has the disadvantage to be an indirect approach by definition, but has the big advantage that for knowing where the cosmic ray comes from, you cannot avoid that, because the cosmic rays are deflected by the magnetic fields, and you lose totally the directionality, while gamma rays do not. So, a couple of words about training the future generation. Training students, so the future scientists, the one that will take on our high-energy astrophysics group when we will be retired in 40, 50 years from now, is a crucial issue. We made explicit a course devoted to high-energy astrophysics that is active in MCTP since 2018, and since this year it has been activated in the program of the Master of Physics of UNACH. This is devoted to master students, but talented bachelor students who escaped were welcome as well to participate. The course that was almost 18 teaching hours basically consists of an introduction to cosmology, particle physics and astrophysics, and it goes more and more deeper into more specific topics of astroparticle physics. These include also atmospheric physics, the physical atmosphere, and gamma ray astronomy. In addition to me, several other professors of MCTP, like Celia, Sarah, and Jorge, that are here with us, and a professor of the faculty, and an external professor, also from Argentina, was invited to teach and their expertise in the courses, and very nicely accepted that they did it with a very big interest of our students. So the next steps, when the students get interested in the high-energy physics, so in the kind of science we are doing in our research group, they come to ask you for a thesis, and we currently supervising several of this work. The first was by Leila, was a bachelor thesis that was getting the top mark in the mention of honor, and the second was a master's thesis by Juan Carlos that is expected to finish in December. The third is a PhD thesis that was expected to finish several years ago. And the fourth, Leila, was likely so much to work with us that currently is started with us a master's thesis. Okay? I will speak in details about the first two jobs in the next slide. Please note that also from these slides appears that MCTP is working really in close collaboration with the Faculty of Physics of UNACH in this respect. There is just a colorful note, because I was thinking it was not worthwhile to spend our time on this. I'd like more to do research and other things. But I was really emotionated by that. We was also involved in advising and judging much younger students. Much younger student means from 8 to 13 years old. I was amazed by them. There was a project that are mandatory to save our planet. I mean, there was one guy that was actually winning the state competition, the Chapas competition. Now he's going to Mexico City for the federal competition, who was trying to make plastic material from the skin of bananas. what can I advise to this guy? 11 years old. Do one like this. I mean, the world needs your job and your idea to be saved. I was almost crying when I was seeing the project of this guy. We was also asked to become the supervisor of this kind of project. Unfortunately, most of the activity here are in San Cristobal, so logistically it was impossible for us. If they will open a second part in Tuxtla, we will work on this. But this is only a colorful note, it doesn't have much to do with the research we are doing in our group. But I'd like to say that the research is not isolated in metaphysics in some fast base. Research is the one that is the main engine to the development of the society. Industrial, technical, social, cultural. Okay. So we have to remember that our job is more important than we think in this respect, because shut the path for the future generation, or at the contrary, can kill them. No? Especially when our ideas go in the hands of the military, as we have seen in the history. No? So let's go to some details to celebrate also the very successful job of some of our students. Laila was working, a big fraction of her thesis was working on the X-Newton X-ray observation of this pulsar. This pulsar was discovered by our friend and collaborator Eric Koppel of Columbia University, and by our other friend Gilles Ferrier of APC Paris in 2008 and 2011 on the top of the integral source. After we got LXTA, another satellite with which we was working a lot, both me and Sarah in the past, is not mentioned in today's report for limit of space, but also because the LXTA is not exist anymore, was deorbited to make a very nice shooting star, and is no more, so we can work only on a kind of data on that. The important thing for our group is that in 2008, Regie is also reporting the very energy emission on the top of this X-ray source. Laila was working in details to produce spectral analysis, and the most important result she got is that she found a clear detection of extended emission, and more important, asymmetric pulsar nebula. So her conclusion was that it's a clear case of pulsar nebula system. And it's evident that everything we see in X-rays, hard X-rays, and TV gamma rays is manifestation of the same cosmic accelerator, of the same system. Moreover, her thesis was finished and successfully defended this year. She already published a paper nuclear, that is going to be, is in press, is going to be published in Nuclear and Particle Physics. It is particularly remarkable for a bachelor student, according to me. And she's also preparing a second publication of her thesis work. Currently, she's she's going to extend her master work in the master thesis, not only with X-Newton satellite, but X-Newton, Chandra, and Fermi-Lat GV gamma rays. So I think that her master thesis is easily at a level of a normal PhD thesis. So I'm very happy to celebrate her because she's really a talented student. Another talented student is Juan Carlos that chose to be the most complex identified very high energy source ever existing. This is called 1841. We also see it in Hawke. And this is basically a source 1 degree in radius in the sky. So basically, this is twice the diameter of the full moon in the sky. If you could, your eye could see gamma, you will see a circle, more or less a circle, that is twice as bigger in diameter than the moon, very bright in gamma rays. Very bright means at the level of the crown. It's a mess. Here we don't know what is doing what. We have inside this field of view 2 supernovae remnants, 3 very high spin downward luminosity pulsars, 2 X-ray binaries, one detected and one discovered by another student of us from Germany. And the main topic, or the main target of Juan Carlos' work is to make the analysis of all the X-ray observations, and you see there are a lot, that are covering all the source, and trying to find possible counterpart for the very energy emission. Probably it's too light, but you see this lighter band. Can you see? Can you see that here there is a band? Is visible? Anyway, the lighter blue you see here is basically all the observation that Juan Carlos is analyzing. It is more than 10 X-ray observation, and it covers as best as possible the region of SJ 41. And is already, most of the X-ray observation is already done by Juan Carlos, so I think that his thesis is improving quite a lot. And in addition to that, you can see this supernovae remnant that is simply wonderful. He detected the pulsar, the Schwiz binary, and in particular, not one of the supernovae remnants, because the observation is not so good, but these supernovae remnants alone is worth 1-2 scientific applications. So, let's go very shortly to summarize the main achievements, a very small fraction of the results we got in these 3 years. I will start with organizing the Cosmic Rheology Beyond Standard Model Conference. It's a bit atypical, but I consider this one of our biggest achievements. We could gather together the very best worldwide experts of the cosmic rheology field, and I'm not exaggerating, are really the very best experts in this small town in the Italian Dolomites. And we made a very successful conference. This led us to the publication of a book. Leila told me that it's open source, but you have several hard copies in MCTP, so you can see how good is the product we could do. Given the success of the first, a few months ago we did the second edition of the conference, and again we could gather the best experts. We could, and the book of the conference, the monograph book of the conference, is currently in the press phase. Finally, the work is finished. I mean, last month, then now it's a year in the press to publish it. So, as mentioned, I mean, according to me, the very best expert in the field, being able to gather them together in the same room was a big success. And the monograph book, you will see them. I hope you will agree with me. Become a very masterpiece. The best expert was convinced by the project, and they took their time to write a small chapter of the book. It really became wonderful. And I hope the second is even going further than the first. Thing that I would have never expected when I started the organization of the second one. In addition to Cosmic Beyond Standard Model, I was the organizer together with Stefan Vessenov of the Hope Science Symposium that took place at the inauguration of the book of the Vogue instruments 2 years ago, and you already have seen all the important information about Vogue by the next talk by Ruben. And I fully agree with Ruben. I think it's the most important Mexican astronomical observer that we have, simply because we have 50% control of the instrument. 50% is American, United States, and 50% is ours. While in other very important observatories like Piaget, the percentage of Mexican controls on the instrument is much fewer. Because as Lucas was mentioning, the core bulk of Auger institutes is located in Europe. So, moreover, we could help the organization to, only to conclude the slides, for instance, we could help Dr. Zepeda to organize a basic American workshop of search for new physics last year, and things like this. This work allows us to work to publish one book, last two. Two are about the cosmic rheology of standard model, one published, one in press, and one is or should have been, because it's not clear to me about what is the progress about this second book, based on the very high level invited speakers we had at the inauguration of the symposium that I organized with Stefan, as mentioned in the previous slides. More important, I mean, even more important than the research itself, when you become professor, is to finding the funds, money, to be able to do your research, to be able to have students, to be able to make trials. I mean, all the collaboration I will very short summarize to you in the previous slides require a lot of duties, and you need also to travel with your collaborators to work back to back with them. So we actually are PI manager of a major cancer fundings of Scienza Basica 2015. Is focused on one of our main activities, so the origin of cosmic rays and the possible role of unidentified energy sources. It's a very massive multi-wavelength project, but also peer project. And the starting is to analyze in multi-wavelength all the high energy sources that you see in this table. So Pulsar Nebula, candidate well Pulsar Nebula, you can see here, and unidentified or very identified very high energy gamma ray sources. As well as the use of English in science, whether we like it or not, our research activities are mainly evaluated by our scientific publications and the metrics related to these publications. In the last 3 years, so since the high energy astrophysics group was born, our group was author of 51 scientific publications. 48 of them were international affiliate journals. They would add even with a very high impact factor. Science is the highest impact factor we have currently in the world. APJ is the third, only behind the Science and Nature. Monthly Notice, Astronomy, Astrophysics, Astroparticle Physics, Experimental Astronomy, Astrophysical Journal Supplement Series. That is very important for the catalogs. We will see them in the next slide, and so on. And 3 of them were conference proceedings. Actually, we didn't have so much time to attend conference, and we should definitely do better in the future for this. Because it's not only important to show science, to do science, but also to show our science to the community. This is even more important for the students, which they have to show their job to find a job in the future. In this period, according to the NASA IDS system, my excitation increased from 8,000. I used my application to get the MCTP professorship as a reference to more than 50,000. My Hirsch factor increased from 43 to 56. And of course, I use my methods here because I was the one, as Eddie was mentioning here, and Arnulf was mentioning, that came here initiating the high energy astrophysics groups. But for sure, the group metrics are even higher since they are my metrics and the metrics of Sara together. So now I will give you very small and very screenshot examples of our activities, and I will put some references, so the ones that are interested can go deeper into that, and the students, if they are interested, they can come whenever they want to us, knocking the door for questions, for thesis, for whatsoever. I mean, our doors are open. So, as mentioned a couple of times in this short report, the origin of cosmic rays is one of our main research topic. This is why it becomes for us crucial to work on the catalogs. So on the collection of all the list of the sources that we know at the different wavelengths. Okay? That is the very first step for making a multi-wavelength comparison. So our group was working intensively on the draft of the second code catalog, and in particular on the interpretation of the TV gamma ray source that Pope was seeing, and even more to the comparison between Pope sources and the sources seen or not seen by the other imaging atmospheric telescopes. And you've seen a very nice example of it by Ruben before. But we was working on also on the 2 most complete GV gamma ray catalog. So the third source catalog, so the complete so far GV gamma ray catalog of sources, and to the first Fermi supernova diamond catalog. So to the catalog that goes exactly in the direction of establishing if these guys can resolve the 100 years old riddle of the origin of cosmic rays, where they come from. Okay? So Another thing is going back, since this, whether you like it or not, working on the catalog is also very remunerative in terms of metrics. So a bet on the catalog for the student is a very good bet, because the catalogs in a few months after the publication they got hundreds of citations. So if you really work on that, it's a very good boarding pass for a PhD position, postdoc position whatsoever. My suggestion. Going deeper and into the core of the audio cognitive riddle, we have to cite a paper of me and Luke Drury. Luke Drury is the current head of the cognitive department at DIAS in Dublin, Ireland, and at that time was also the president of the Academy of Sciences of Ireland, and the one with the former director of Stanford University. And they also mentioned the catalog of supernova remnant, and this is an ongoing work. In fact, there was just accepted a paper by Sarah and myself that once more, this is a major topic in the history of my career, showing that very old puzzling nebula are a natural explanation for unidentified TB gamma source. At this point, we don't have time to go in details. I can speak 1 week consecutively about this topic. Trust me. Of course, in all our activity, we should remember that we couldn't do everything in 3 years. Our activity, for instance, about technical auditing, started way before we came to MCTP and created astrophysics groups. And for this kind of research could become crucial bricks in the building of the group, and hopefully also the building of MCTP as it wishes by Eli before. So, going far away, I was mentioning that AGNs are also an important side of our research. Historically, this is also a very clever reason, and this again goes to the very smart question you asked before to look at. At 1 PeV energies, the galactic magnetic field seems to not be enough anymore to confine the protons, the cosmic rays. So naturally the people, and casually at 1 PeV we have the feature in the cosmic spectrum that goes from a slope of 2.7 to 3, it's called the knee. And that feature is the one at 18 called the ankle, because the slope is going back to the previous 2.7. So studying stellar sources was seeming a natural path to study the higher energy part of the cosmic rays. Okay. Lucas was speaking extensively about this, so I hope I don't have to go in detail with that. I used the past, it was not causal mix, because actually Fermi-Lab and the new experiment that should have solved the question was completely messy in time. Nowadays, we really do not know what is doing what. The very big summary of this conference was given by Luke Drury, by Roger Lefford, the former director of Stanford, who stated in one sentence, on Monday, we was told, he was speaking about the conference plan, that all the cosmic rays have a galactic origin. On Tuesday, we was told that all the cosmic rays have an extragalactic component. Well, now it's Wednesday, I'm confused. It's really a hot topic, and what should have applied the questions didn't, and make more questions and more complicated. So in this optic, also studying very different objects from the galactic object is becoming important. We got something like 10-15 papers on this topic, and I mentioned this one because it was leading to totally unexpected discovery, or more conservatively speaking, interpretations of what can be the real process of acceleration of particles exactly on the black hole event horizons. But And there is not only, it's not so different, the topic from extragalactic to galactic. In fact, a major part of our extragalactic effort goes to study narrow line secret one galaxies. That seems to be the conjunction link between the most powerful active galactic nuclear lasers and similar, physically similar and geometrically identical accelerator we have in the galaxy. So X-ray binaries, in particular, they support galactic nuclear lasers. So we worked a lot with Luigi on this paper that is the most complete multi-wave survey of narrow line secret one galaxies. In this paper, we studied 42 radio loud narrow line secret one galaxies. And this is so far the most complete sample we have in this field. So, as mentioned, this is only a short example. We did work also, these are first minor activities for our group, because what I show you so far is more than enough for 2-3 research group. We did work, despite this, also on binaries, flat spectrum radio quasars, and we worked on building the future observatory. The Astrodome white paper should be submitted next month, and we worked on exactly the supernova element cosmic radiology part of this white paper. We had a special issue on experimental astronomy journal on GEM-EUSO. We worked on the magic of grade, etc., etc., etc. We cannot speak about everything. So this very short sample of articles and very small hints of research we are doing in the astrofisica group and MCTP is over. As mentioned, it's important not only to use the old data, but to successfully ask and gain new observation that should answer the question we have in astrophysics that the previous observatory and the data could not answer. We was quite successful in the X Newton announcement of 2015, and we got two galactic project approved, and we got observation time with X Newton. I said very successful. We was submitting 4 proposals, 2 was accepted. So 50% success is much more than 1/6 that is the general success rate for X Newton. So this year was particularly successful. To balance it, in 2016 we got 0% success rate. One is a pulsar nebula, that could be instead a supernova remnant ring interacting with a molecular cloud system, with a molecular cloud. And then another is more confidential because it is observation experiment strictly correlated with 2 cold suns. That is not published, so this is what I can say. But we keep to be the leader, project leader of major project that was performed just before we came to Java. For instance, the major observation campaign on 1H0323, now 971 galaxies, was class A ranked integral, very large integral observation set. We got additional Swift screenshots, optical telescopes, radio telescopes, and of course the gamma ray telescope, Fermilab, and TV challenge telescope was also covering the source in the same period. Last slides, but not least, it seems that we are going in the right direction, as Eli was asking before. In fact, it seems that our research is appreciated at national level and international level. In fact, in these 3 years, we have been often invited to national and international institutes to show our research results. ICTP, Udine University, Trieste, Grupo University in Germany, Roma, La Sapienza, and Tor Vergata, Castle Institute of Technology, Simberstar, Mexico City, Università Michoacana, San Nicolás del Lago, Morelia. So people like what we are doing and invite us to show this. This is only a small sample. I mean, this week we are invited, or better, we would have been invited in Ecuador. In September, we are invited in the CMC conference in Pachuca. in October, as mentioned at the beginning of the talks, we are invited to open astronomical meeting in Belgrade, in Serbia. So it's taking away time on research time, but it's also nice to show your results